Alrighty, welcome back everyone. In this video, we're going to do some more examples of using the first derivative test. And I'll remind you that the first derivative test is really for doing two things. First, for finding intervals of increasing decreasing, and secondly, for classifying critical points. So in the examples we do today, I'll do both of these for each of the functions that we consider. Alright. So here's our function, x squared minus 3 times e to the x. So the first thing I have to do, as has been the case in every problem we've done in chapter 4, is to take the derivative and find out where it's 0. This is a product rule because these two things are being multiplied together. So here's our derivative. And I need to find my critical numbers, so I need to figure out when this derivative is 0. Helpful thing is to first factor out an e to the x. So if I factor out an e to the x from everything, I'll get an e to the x times 2x plus x squared minus 3. Okay, there's an e to the x in this term and an e to the x in that term, so when I factor it out, I get this. Now I can rewrite that. All right, so remember e to the x is never 0, it's always positive. So I'm not going to get any zeros of the derivative for this. Here I'll get x is minus 3, and here I'll get x equals plus 1. Those are my critical numbers. So now I'm going to put these numbers on a number line. Just like that. And then I need to go ahead and pick my test points. So that is, I need to pick a point somewhere in here, about 0, a point over here, how about 2, a point over here, how about minus 4. And I need to plug these test points into the derivative. Okay? And I want to remind you, before I plug these into the derivative, that I simplified the derivative down to this. So I can keep this as the way that I'm writing the derivative. Okay, so plugging in minus 4 here, we get e to the minus 4 times 16 minus 8 is plus 8 minus 3 is plus 5. 5e to the minus 4th, that is positive. Remember, e to every power is positive, even if the power itself is negative. If I plug in x equals 0 to the derivative here, then I get e to the 0, which is 1, times minus 3. So this is minus 3. And so here it is negative. And when I plug in 2 here, I get e squared times 4 plus 4 is 8, minus 3 is plus 5. And so that is positive. Okay, so here is my derivative profile. Now, once I've done that, I translate this into a profile for the function f. Namely, I remember that positive derivative means increasing and negative derivative means decreasing, so all I have to do here really is write upward pointing arrow, downward pointing arrow, upward pointing arrow, like that. And so, if I want to summarize that, I can summarize this answer in terms of what I've learned about increasing and decreasing. Namely, this function is increasing on the interval minus infinity to minus 3 and 1 to infinity. And it is decreasing on the interval minus 3 to 1. What about critical numbers? How do we classify those? Well, we have one critical point that starts with minus 3, one that starts with 1. I want to write down the y-coordinates of these. Remember, to write down the y-coordinates of these, I have to go back to my original function. In this case, my original function was x squared minus 3 e to the x. So this minus 3, its y-coordinate was 6e to the minus 3. In this 1, its coordinate was minus 2e. And so looking back at our diagram, which was this critical point, local min, local max, or kink? Well, looking at the shape of the graph here, that looks like a local max. I know that because here the function switched from increasing to decreasing, which is going to make this upside down u. Likewise, at 1, it switched from decreasing to increasing, so that's going to make this right side up u. So this is a local min. Let's look at g of x equals x plus 1 divided by x squared plus 2x plus 2. So, what do I have to do? I have to find the derivative first. So then g prime of x is going to be a prime b minus ab prime. All divided by x squared plus 2x plus 2 squared. And so after a bit of simplification, there's our derivative. Now I want to find the critical numbers, and the critical numbers are going to be the places where the derivative is 0. And I'm going to look for those out of the numerator here. So I'm going to solve the equation minus x times x plus 2 equals 0, which is going to give me x equals 0 and x equals minus 2. These will be my critical numbers. This is not going to be relevant for examples that show up on future exams, but I will point out that because this fraction has a denominator, you might worry that this fraction actually has an asymptote somewhere. And if the graph had an asymptote somewhere, then this whole process would end up being a bit more complicated. Namely, we'd have to split our number line at each asymptote. Again, I promise that's not going to come up on the test or the final, but I just want to note, because there's a chance if you go on and take 141 or something like that, that detail will become relevant. So, we need to mark our critical numbers onto our number line. Those critical numbers were 0 and minus 2. And then remember, we need to dig out our test points. So I'll pick as my test points 1 and minus 1 and minus 3. And I need to plug these into my derivative. Remember, I have this form of the derivative, which is probably nicest. So this is minus 1 times 3. That would be minus 3 divided by 5 squared. Sounds like minus 3/25 to me. G prime of minus 1. It'll be 1 over 25. And g prime of minus 3. That will be minus 3 divided by 17 squared. Now, remember, I don't really have to simplify these numbers. All I have to know is whether they're positive or negative. And so this one is negative, this one is positive, this one is negative, and that is what I need to make my derivative profile. Translating all of this to information about the original function, I'll go ahead and make up this profile. And so here the function was decreasing, then increasing, then decreasing. Again, negative, decreasing, positive, increasing, negative, decreasing. And so that lets me answer my question about what intervals the function's increasing and decreasing on. We have just one more thing to do, which is to classify the critical points. And again, I can classify the critical points just from looking at this profile that I made of G. Namely, here I see that at minus 2, the function switches from decreasing to increasing, which makes this upward pointing U shape. So this is a local min. And then at 0, it switches from increasing to decreasing, which makes this upside down U shape, which makes this a local max. All right, let's do one more example of this, and then we'll do some examples of other ways of thinking about the first derivative test. So now let's work with the function x cubed times the natural log of x. When we go to take the derivative here, we'll need to use the product rule. And so when we go ahead and do this, we'll get this a prime, b prime. And so this will be a prime b plus ab prime. And we'll work to simplify this a bit. And we'll notice at this point that I can factor out an x squared, just like that. Now, I want to know when this is 0, because that will give me my critical numbers. So this happens when x is 0, or when 3 times the natural log of x plus 1 is 0, which is when 3 times the natural log of x is minus 1, which is when the natural log of x is minus a third, which is when x is e to the minus a third power. So my critical numbers in this case are x equals 0 and x equals e to the minus a third power. So we'll make up our number line for our derivative profile, label it with our critical numbers, and we'll go ahead and label some points in here. And so we might have to think for a second, okay, how big is e to the minus a third? Well, e to the minus a third is 1 over the cube root of e. And what this tells you is that this number is less than 1. Because the cube root of e has got to be bigger than 1, because e is bigger than 1. So I can choose as my number over here 1. On the other hand, e is definitely bigger than the cube root of e, so I can choose as my point over here 1 over e. Or e to the minus 1, if you like. And so you can convince yourself this is e to the minus 1, this is e to the minus a third, this is e to the 0. These indeed work to choose these numbers in this order so that I can have my test points. So now I'm supposed to plug these things in. Remember, I have my nice f prime of x written out here. So when I go to plug in 1, I'll get, 1 times 3 times the log of 1, well, that's 0, plus 1. So it's just 1. Okay, so in other words, it's positive. When I plug in 1 over e, I'll get 1 over e squared times, and then the log of 1 over e is minus 1. So minus 3 plus 1, that would be times minus 2. So this is negative 2 over e squared, so that's negative. And what about when I go to plug in minus 1? Well, I'm going to get 1 times 3 times... Oh, but wait. The log of minus 1 is undefined. So in fact, actually, if we back up a second, the derivative here at minus 1 is undefined. Actually, the derivative here at every point less than 0 is undefined, because log of negative is undefined, always. Now, in fact, if you look, actually, the problem runs deeper than that. The original function had a log of x in it. And so, in fact, actually, at all the negative inputs, this function is undefined. So, in fact, what I really should do is just x out this entire piece of the function. This function is undefined anywhere less than 0. And so, as a result, I just don't have to think about that. The function's not increasing and it's not decreasing to the left of 0. In fact, if you go ahead and think about it for just a second longer, you'll realize that actually at 0, which we said was a critical number because when we solved this, we got x equals 0, the function's actually undefined there too, because log of 0 is also undefined. And so actually I can also x out that 0. So there's a little bit of a twist there at the end with some of the function being undefined, but largely speaking, we can just go about our business the way we have been. So the function is going to be decreasing on 0 to e to the minus 1/3, and increasing from e to the minus 1/3 out to infinity. And note it's nothing from minus infinity up to 0. If you want, you don't have to include this, but if it makes you happier, you can write that it's undefined from minus infinity up to 0. We're going to wrap up this video here. In the next video, we're going to go over some more conceptual questions that involve the concepts behind the first derivative test. But that's all for now. I'll see you next time.